Hello, let's talk about gravity. So don't get intimidated. I know this is doesn't look as scary as an equation written out like this, but either way, I know it's still a lot going on, but we'll talk through it. So Newton's law of gravitation um, explains the gravitational force between two objects. So it's the force. This symbol here means proportional because we're missing a constant that we're going to multiply this by. Um, so force is proportional to the mass of each object divided by the distance between them squared. So like here's an example of just two masses, they're circles. And so each of their masses contributes to the force between them, and so does the distance between them. Now let's look at it like the equation itself. So like I said, don't get intimidated. We can handle more complicated equations. So F for force, we're familiar with that. Ignore this G for a second, and then it's just mass of object one, mass of object two divided by the distance between them squared. Okay, all we did was simplify. Instead of writing out the words, we gave them labels. And then this G, this is that constant I was talking about. So this is called the universal gravitation constant. And it's super tiny. This is times 10 to the negative 11. Really tiny. Because gravity is actually a pretty weak force. The reason we experience it holding us to the surface of the planet Earth is because our planet, Earth, is extremely massive. 10 to the 24 kilograms to be exact. So even though gravity is a pretty weak force, when objects are really massive, it counteracts the kind of weakness of the force. Okay, so this is our equation for the force, right? Force is this constant times each mass divided by the distance between them squared. Okay, but we have talked about the force of gravity before. We've talked about the weight of objects, right? And so you're probably wondering, how does this relate to the weight of objects? Well, it's actually the same. Okay, here, let me add my little labels. So the weight of gravity near the Earth's surface, the thing we've used, little m, or the mass of the object, times g, the free fall acceleration or gravitational acceleration, or 10 meters per second squared, is equal to the universal force of gravity when we plug in the mass of the Earth and the radius of the Earth. And then this mass is still the mass of our object. Okay, so I know this is like an intense amount of equations, but remember, you already know this side. This side is just the weight. And this is the new thing we're learning. And what I want to show you is that since the mass of whatever the object is on both sides, we can actually cancel that out. And then we get this equation for little g. That is big G times the mass of the Earth divided by the radius of the Earth squared. So I'm going to plug all that in. Don't worry, it's going to look overwhelming because it's in scientific notation. But the important part is this over here that comes out at the end. If we plug in our value for big G and the mass of the Earth, like I said, it's 10 to the 24 kilograms, and then we divide by the radius of the Earth squared, we get 10 meters per second squared. So this is actually where the little g we've been using comes from. It comes from this universal force of gravity equation for the Earth itself specifically. So I know this slide overwhelming, but again, we've actually been working with this half of it and little g itself, and this is just interesting. It shows us where this came from. So let's talk a little bit about weight, actually. If you stand on a scale at rest, which most of the time is true, your bathroom scale is not usually moving around, it reads your weight. But if you're accelerating in the vertical direction, like if you put your bathroom scale on an elevator, the scale reads how much force you exert on the scale, which depends on how much you are accelerating and in which direction. So we can look at this example of someone standing on a scale in an elevator. When the elevator is moving at constant speed, so that's this one, they're just, sorry, I'm trying to see if we can actually tell if it's at constant speed. I guess, yeah, that's fine. That normal weight is telling us there's no acceleration in the vertical direction. So this would be like when your scale's in your bathroom instead of in the elevator. The scale's just going to read your weight as it normally would be. But when the elevator is accelerating upward, the scale reads a larger weight and the person feels heavier than normal. So if we're accelerating up, the scale is going to read a bigger number, bigger value, and you feel heavier. That's because the force pushing up on this person in the elevator is larger than the force that they apply downward. And then when the elevator accelerates downward, the scale reads less than the normal weight of the person, and that person feels lighter. That is because the force pushing up on them is smaller than the force they apply downward. And remember, that part is important about which direction the overall force or that net force is acting, because that tells us if there's acceleration, right? So for this example of the accelerating upward, the force pushing up on the person's feet is bigger than the force they push down, or also the bigger than the force they feel from gravity. And that's how we know accelerating upward, and then the opposite for accelerating downward. And then this final example is when the cable breaks and the elevator is in free fall. In free fall, you feel weightless because there are no support surfaces holding you up and making you feel your weight. Weightlessness is really just falling. When people want to experience weightlessness, they go in an airplane that goes into free fall so that they experience temporary weightlessness. And astronauts in the International Space Station are constantly in free fall because orbits, which we'll talk about in the next lecture, are really just falling around a gravitational object. Let's talk about the ocean tides. So, the ocean tides are caused by differences in the gravitational pull between the Earth and the Moon on opposite sides of the Earth. The pull is stronger on the side that's closer to the Moon and smaller on the side that's farther away. So low tide, the water is drawn away from, like, let's say it's low tide for us, excuse me. It's not the same all over the planet. But let's say it's low tide for us, that means the water is drawn away from this side of the Earth because the Moon is on the opposite side of the Earth. So it's pulling the water over there. And then when it's high tide over here, the water is drawn to this side because the Moon is on this side of the Earth. And this is happening because during the day, the Earth is spinning on its axis. So the side of the Earth closest to the Moon changes throughout the day because one spin of the Earth is a day for us. And the sun also contributes some gravitational pull on the oceans, but the difference in distance between one side of the Earth and the other is really tiny compared to the distance between the Earth and the sun. But when we look at the distance between one side of the Earth and the other, and the distance between the Earth and the sun, the tides tell us that that difference from one side of the Earth to the other is significant enough to cause the tides. And this is also, which this is a fact that I just find really interesting. This is all also why there aren't tides for smaller bodies of water. There isn't a big enough difference in the distance from the moon. But because the oceans cover the whole surface of the planet, um, it works that way. Um, so anyway, that's just an interesting extra tidbit. Now, with respect to gravity again, well, I mean, that was about gravity too, but now we're talking, um, I guess it was also about the moon. So anyway, we have an indestructible person who's standing on a shrinking star. The force of gravity they experience depends on their distance from the center of the star and their mass and the mass of the star. Like it's just this equation that we just learned, right? It's the mass. Let's say this mass one is the mass of the star. Mass two is the mass of our indestructible astronaut. And then distance here is the radius of the star or the distance from the center of the star. So if the star shrinks by half, that would be it collapsing into itself some. The distance between the person, or excuse me, the indestructible astronaut, and the center of the planet, or sorry, it's a star. That was accidental mistake. That distance decreases by half, and that makes the force they experience increase by 4. And that's because when we decrease, remember, a smaller number on the denominator means a bigger number overall, for one thing. So that's like the first thing. If we're making the distance smaller, we're making the force bigger, but we're also squaring it. So we're making it even smaller down here and even bigger overall. If our star continued to shrink, oh, sorry, no, I missed what I was going to say. If this, oh no, it's Friday for me, so sorry about that. If the star continues to shrink, the force of gravity on the surface will continue to grow, and it will be harder and harder for our indestructible astronaut to escape from the surface. The escape velocity is the velocity required to escape from the gravitational pull of a planet or a star. If our star continued to shrink, eventually the velocity needed to leave would be larger than the speed of light, and the speed of light is the universe's speed limit. Nothing can travel faster than that. So when that happens, when the escape velocity is faster than the speed of light, we end up with a black hole. And here is an actual image of a black hole. And you'll notice this bright ring and then darkness in the center. That region in the center is where the escape speed is greater than the speed of light. So even light can't get out. And this black hole is an image of the black hole at the center of this galaxy. Over here, this galaxy is M87 or Messier 87. It's just named after a survey. It's like the 87th object of the Messier survey. And this is an elliptical galaxy, which is different than our galaxy. The Milky Way, our galaxy, is a spiral galaxy. So it has a lot more dust and gas than an elliptical galaxy does. But back to the black hole. So again, there's this disk of material around the black hole because these objects, and again, we're going to talk about orbits in the next lecture, but the material is orbiting around the black hole and moving really fast. And that's why we see it as so bright. But then that material, depending on how close, once it gets to this dark region, it's not coming back out. But because there's material moving so fast in orbit of the black hole, what we end up with is actually this jet here. That's what this is. That is coming from the material trying to go into the black hole. So that can sometimes happen, is it will accelerate things so much that as long as it's not within the region where it has to move faster than the speed of light, it can rocket that stuff out. So that's all I have for you this time. Oh, well, sorry, one more thing. This black hole is 3 to 6 billion times the mass of our sun. Okay, that's the last thing. See you in the next one.